Yeah, so my name is David, and I'll be presenting Accelerating File System Checking and Repair with pFSCK. And this is work that I've done with Sudarsun Kannan and Stratton, also at Rutgers University. So to start off, what is file system checking? Right? File system checking is used to ensure a file system's metadata is consistent. And it does things like checks whether file system tree is connected, whether file and directory metadata is not corrupt, and also check whether all data blocks are accounted for. In general, file system checking is done in the event a file system is left in an incorrect state. And this because this could be due to a system crash or a buggy file system, or an error in the storage hardware, such as a random bit flip. Right? So to continue, in most cases, file system checking is referred to as FSCK, or short for file system check, and they come in online and offline forms. However, the most common form is offline, and in the past, they have been historically notorious for long running times. And this is problematic as it can incur large downtimes and be a hassle for system administrators. So on the other hand, modern storage and consistency mechanisms has also evolved since the file system checker has been conceived. First off, modern storage has evolved since hard drives. For example, newer storage technologies like Intel Optane and NVMe provide higher bandwidth capabilities as well as lower latencies. And there also have been many developments to support crash consistency and recovery. We have things such as journaling, copy on write, and erasure coding. However, mechanisms such as journaling and copy on write cannot detect such silent bit corruptions. And for erasure coding, reconstructions and resharding of data can be quite time-consuming. To make things worse, dense flash storage such as multi-layer cell technology has been shown to be prone to cellware and bit corruption. In the end, we can see that file system checking, offline file system checking to be more specific, is still relevant, and there's still room for improvement. Which brings us to our proposed system, pFSCK. So pFSCK provides parallelism for file system checkers at a fine granularity, for example, inodes. And it does this as well as ensures correctness through logical reordering by delaying dependent checks, and adapts to different file system configurations by using a dynamic thread scheduler that balances work in an optimal manner. To clarify, by different file system configurations, I mean file systems with differing amounts of utilization, such as file counts and directories. Overall, pFSCK shows a 2.7x improvement over vanilla FSCK and a 1.8 to 8x improvement over XFS repair. Now later, as we go more in depth into pFSCK, we'll see that there's several challenges that arises when we try to parallelize file system checking. We see that the main challenges are isolating global data structures and context among the file system checkers, overcoming dependencies across multiple passes, and finally, enabling effective CPU utilization as well as exploiting disk bandwidth. So just a little bit of background. This is probably something that most of you already know, so I won't go into much detail. Right? So here we have the traditional ext disk layout, which consists of 6 parts. Right? We have the superblock, group descriptor, bitmap, block bitmap, inode bitmap, inode table, and data blocks. Right? And this is just one block group of multiple block groups on a disk or partition. Right, so to continue on to file system checking, right? So the Linux ext file systems use FSCK, and FSCK checks for any inconsistencies by using 5 logical passes. In these passes, it scans through all file system metadata and checks the integrity of the metadata objects as well as consistency across the metadata objects. In general, FSCK builds its own view of a consistent file system in order to repair the actual file system. Now, to recall, FSCK consists of 5 logical passes. So the first one checks inodes, the second one checks directories, the third one checks connectivity, the fourth one checks reference counts, and the last pass checks cylinder groups. So there are currently a few approaches that exist to aim to improve the way file system checking performs. First off, FSCK can actually parallelize checking across disk or partitions. XFS repair, which is the file system checker for XFS, can parallelize file system checking across allocation groups. However, for both these approaches, parallelization is limited to a coarse granularity and can potentially cause issues. Let's take the case of XFS, for example. So XFS can parallelize across allocation groups, where allocation groups are independent structures that store files and data. At first, allocation group utilization might be quite even. However, over time, file system aging may cause an utilization imbalance. In this case, checking runtime would be limited to the most heavily used allocation group. And overall, allocation group imbalance would limit threading benefits. As for other approaches, FSCK modified the file system and rearranged metadata blocks which provided minimal seek times for faster scanning. chunkfs, on the other hand, partitions the file system in smaller isolated groups, which allowed these groups to be repaired in isolation. Finally, SQCK uses declarative queries and databases for consistency checks that allows for more expressive fixes with comparable runtimes. However, FFSCK and chunkfs requires extensive modification to the file system. And SQCK requires a complete overhaul of the checker itself. Now for some motivation. So to understand the complexity of FSCK, let's take a look at the current performance. To do this, we took a system with 2 Intel Core CPUs, 64 gigabytes of memory, and a 1 terabyte NVMe flash storage. And then we ran FSCK against 800 gigabyte file systems of varying configurations. For the first experiment, we varied the file count, keeping the file count constant. And for the second experiment, we varied the directory count, having at least 1 file per directory, with each file size, the file size for each file also remaining constant. Right, so we'll look how FSCK performs with varying file counts. So on the bottom, we see the file count in millions, and on the x-axis, y-axis, we see the runtime in seconds, right? So first, we see with 10 million files, the runtime is around 23 seconds. And as we increase the file count, we see that this trend continues. So based on this, we can see that the runtime scales linearly with file count. Also, we can see that the directory checking pass runtime also increases because as the more files are added, more directory entries are added as well that needs to be checked in the directory checking pass. Next, let's look at directory count sensitivity. So on the x-axis, we have directory count in millions, and on the y-axis, we have runtime in seconds. So to start off, with 5 million directories, the runtime is around 100 seconds. And then as we increase the number of directories, we see it increases to around 500 seconds. Based on this, we can also see that the runtime scales linearly as well with directory count. We can also see that the effective runtime is significantly longer than a file-intensive file system. And this is due to directory pass runtime dominating due to the directory block checksumming. So some takeaways and research questions. Right? So we saw that the current file system checker runtime scales linearly with file system utilization. We also see that current file system checkers do not exploit modern storage performance because all passes are done sequentially, and file system checkers fail to support fine-grained parallelism. In light of these takeaways, we want to answer, how can we speed up file system checking and repair without compromising correctness? Also, how can we adapt to different file system for different file system configurations, such as a file-intensive file system versus a directory-intensive file system? So it turns out we can do this by parallelizing file system checking at a finer granularity, such as inodes or directories. And overall, we should overlap as much independent logical checks within each pass, overlap as much logical checks across the passes, reduce any contention on any shared data structures, and last but not least, efficiently manage work for threads across passes. So on to the design. So before we get into it, let's take a look at the serial execution of FSCK. Within each pass, FSCK serially checks the file system metadata. For example, in the inodes pass, it checks the inode structures. While it does this, it also updates global data structures to generate a view of the file system based on the metadata it has seen. Lastly, FSCK generates work for the next pass. For example, in this case, the inode checking pass creates a list of directory blocks to be checked in the directory checking pass. Now, in pFSCK, execution is improved with data parallelism. With data parallelism, metadata is split into smaller groups, and a pool of threads is used to check these groups in parallel and generate intermediate lists. Lastly, these lists are aggregated, and the process repeats in the next pass. However, modifying FSCK to do this still poses some challenges. In the case of FSCK, it stores data in buffers needed for execution. And these include block buffers to store blocks that it wants to read in, a block cache to store recently read blocks, and a problem context that gives contextual details in the event of a failure or an issue. So a naive solution to this would just to be serialize accesses across the threads using locks. However, this would reduce the total amount of concurrency that we can achieve. In order to resolve this, pFSCK introduces what we call per-thread context. In this case, each thread context stores its own buffers, cache, and problem context. With this, threads are able to operate in parallel as we would expect. However, even with per-thread context, there are still some issues because not all global data structures can be isolated. Let's take, for example, this block bitmap, which tracks the blocks being used. This is needed, and it has to be stored globally for consistency checking between inodes and ensures no two files reference the same block. Because of this, synchronization is unavoidable without a complete redesign of FSCK, and ultimately, it limits the amount of concurrency in each pass. However, this is where pFSCK's pipeline parallelism comes in. Instead of resolving contention on these shared data structures, what we can do is hide the data parallelism synchronization bottlenecks. And we can do this by allowing multiple passes to operate in parallel. This would effectively increase the amount of metadata being checked across passes instead of just a single pass. So in order to enable pipeline parallelism, we turn each pass into independent flows of execution, use per-pass queues to store inputs from previous passes, and with this architecture, we can continuously feed. First, we have to have multiple thread pools for each pass. And then with this architecture, we can continuously feed subsequent passes with metadata. Finally, pFSCK doesn't wait for previous passes to complete and speculatively carries out future checks. Notes the emphasis on the speculative nature of this kind of execution, as there still may be issues in previous passes that nullify the validity of checks in the subsequent passes. So this speculative checking actually introduces what we call the dependent check problem. In this case, some logical checks depend on information generated by the previous passes. For example, in pass 2, directory checks are verified. To verify directory relationships, we must check that any subdirectory must have a reference to the current directory. A simpler way of saying this is that if you can navigate to one subdirectory, you should be able to navigate back to where you came from. However, this cannot be done until both the parent and the subdirectory's inode has been checked. A naive solution to this would be to wait for dependent information to be generated from the prior pass. However, the potential issues is that it could stall working threads indefinitely. So a better way to solve this issue would be to delay these dependent checks. And this is what pFSCK does. During execution, pFSCK delays dependent checks and marks them as intermediate tasks to be carried out later. pFSCK then executes these checks once the previous pass is finished. This ensures checks are eventually carried out for correctness and prevents any threads from stalling. And just a disclaimer, there are just a few complex edge cases that exist in subsequent passes that are not easy to delay. These complex edge cases is something that we're still currently investigating to see how we can solve these. So even with pipeline parallelism, we still face the issue of work imbalance, as we saw before. In this case, different file system configurations can cause work imbalance between the passes. And because of this, it's not very straightforward how we should assign threads to each pass. Let's take, for example, pFSCK running with 3 threads. For a file-intensive file system, the majority of checking would be done on inodes. However, you can see here there's many inodes that need to be checked, but there's more threads within the directories pass. Looking at a directory-intensive file system, maybe there may be more directory blocks that need to be checked, but then more of the threads are assigned to pass 1. In this case, we need a mechanism to migrate these threads, right? So our solution that pFSCK uses is a dynamic thread scheduling. The main idea is to calculate proportions of work among the passes and redistributes the threads. To do this, a scheduler thread periodically samples the task queue lengths of each pass. It then calculates the total amount of work that needs to be done with normalized weights. These weights are used to normalize the work between the passes. In this example, we'll use the weights of 1 to make it simple. After the work has been calculated, the scheduler calculates the proportion of work for each pass. And after that has done, it then calculates the thread distribution and then redistributes the threads. In the end, dynamic thread scheduling allows pFSCK to adapt to different file system configurations with differing metadata densities. So lastly, we'll realize further optimization with FSCK opt. FSCK opt is further optimization for the serial FSCK in addition to pFSCK. In this case, we found that there was a repeated string localization for every metadata object that incurred very high overheads. More specifically, we found that it called the DCI get text function from the glibc library a significant amount of times. And the purpose of this translation was to give contextual information in a preferred language when an inconsistency was checked. To solve this, what we did was to cache translations instead of relocalizing the string for every metadata object. Since the discovery, we have reported this, and it has been fixed and released within the current release of E2FSprogs. Finally, to conclude the design, we'll discuss what happens with pFSCK when the file system has errors. In general, when errors are detected, threads are serialized. The thread that detected the error fixes the error if possible. Then, once the fix is complete, all threads continue in parallel. In our experimental testing, even with errors, pFSCK outperforms the serial FSCK. However, to make sure this is true, we are conducting more exhaustive testing. Now, on to evaluation. So in our evaluation, we'll try to answer the following question. Does pFSCK's fine-grained parallelism improve performance? And can pFSCK adapt to various file system configurations? For our methodology, we use the same system as we used before. And as for the tools that we used FSCK, which is in the version 1.44 release of E2FSprogs, and XFS Repair, which is in the XFSprogs release 4.9. And then we have pFSCK, our proposed solution. First, we want to evaluate pFSCK's data parallelism compared to the vanilla FSCK and XFS Repair. In this part, we use the following configurations. So here we have FSCK, which is the vanilla FSCK for ext file system, FSCK opt, which is FSCK but serially optimized, and then pFSCK with data parallelism with various thread counts, and XFS Repair, which is the XFS file system checker with various thread counts. So first, we'll evaluate the performance on a file-intensive system. So here on the x-axis, we have FSCK, or the different configurations, and on the y-axis, we have the runtime. For the vanilla FSCK, we see that the runtime ends up being around 81 seconds. We see that this decreases with the optimized FSCK and improves by around 20 seconds, yeah. Lastly, we have pFSCK that improves runtime and ends up being around 42 seconds with multiple threads, more specifically 4 threads. Based on this, we see that pFSCK's data parallelism improves performance by 2x. However, not shown here, data parallelism alone improves performance over XFS by 1.8 to 8x. Note that we don't have XFS here to show, as we see performance variation on NVMe for different images and thread counts. And this is something that we're currently looking into and something that we should have an answer to soon. Lastly, we see that pFSCK data parallelism actually does not scale past 4 threads due to contention on shared structures. Next, we evaluated these configurations on a directory-intensive file system. So first, we see that vanilla FSCK takes around 300 seconds, and the serial XFS takes around 60 seconds longer at around 326 seconds. Next, with the optimized FSCK, we see a little bit of improvement. And then as we go on, XFS doesn't really improve at all, but we see some improvement with pFSCK. Based on this, we see that data parallelism and optimizations alone improves performance over vanilla FSCK by 1.4x. We also see that data parallelism alone improves performance over XFS by 1.7x. Finally, like with file-intensive file system, pFSCK doesn't scale past 4 threads due to contention on shared structures. Next, let's look at pipeline parallelism. Here, we want to see how effective pipeline parallelism is, performance is compared to just data parallelism. So here we have 3 different configurations. Data parallelism, which is just data parallelism, and then we have a half-half configuration, which is data and pipeline parallelism, with half the threads checking inodes and half the threads checking directories. And then we have a best case configuration where we have the static best case thread assignment. So for a file-intensive system, here on the x-axis we have the thread count, and on the y-axis we have the runtime. We see that with just data parallelism, we see what we saw before and doesn't scale past 4 threads. And for pipeline parallelism with half the threads, a half-half distribution of threads, we see a good amount of improvement. And then finally, in the best case, we see around the same amount of performance, but a little bit better as we increase the number of threads. So here we see pipeline parallelism improves performance by 1.3x and improves over vanilla FSCK by 2.5x. Lastly, we want to evaluate the performance improvements of the dynamic thread scheduler. So in this experiment, we compare the half-half configuration that we saw from the previous experiment, the best case static assignment that we saw from the previous experiment, and then we have this third scheduler configuration where we have the dynamic thread scheduler automatically assigning thread configurations. So for a file-intensive system, here we have a thread count on the x-axis and runtime on the y-axis. We see that just the half-half, it's all right. But then with the best case, it's basically the same. But however, with the scheduler, we see that it's able to overcome bottlenecks in just pipeline parallelism and kind of reduce the performance degradation. So in this case, we found out that dynamic thread scheduler was able to find an optimal thread assignment automatically. And we can see that the scheduler has more impact as the number of threads increase. Finally, we see that the performance increases the runtime over pipeline and data parallelism by 1.1x and over vanilla FSCK by 2.7x. So in summary, pFSCK provides fine-grained parallelism for file system checking. Data parallelism allows for more metadata to be checked at a time. Pipeline parallelism overcomes data parallelism bottlenecks. And then finally, dynamic thread scheduler helps pFSCK adapt to file system configurations. In the end, pFSCK is able to provide 2.7x performance over vanilla FSCK. And to conclude, we see that fine-grained parallelism is required for lower checking and repair times. We see that it's also required to exploit the modern storage capabilities that we have today. In the future, the things that we plan to do is adapt pFSCK for online file system checking, which is quite popular nowadays, as well as apply pFSCK approaches to other file system checkers. And with that, I'll conclude. Any questions?
All right. Christoph, you win.
The usual suspects. So first, thanks for the work. I think it's pretty interesting. And to make us Linux people happy, we'd be glad if you could just dump it out to the mailing list once you've got a few papers in or so.
Okay.
And the kind of question I'm interested in is that's always good for these slides or papers is, how much additional complexity in the tools, and I think you're patching E2FS procs, are you introducing for this? It's like, how many lines of code does it edit? How much more memory usage? Because there's always trade-offs.
So in this case, the amount of lines of code would be around like 500, not even. More like we used very simple structures, and I guess the most code was contributed to the scheduler part, which was the most complex out of all of them. And finally, when it comes to memory utilization, we actually saw that it doesn't scale with the amount of threads that we have. It's not very significant. If we look at the memory utilization, it kind of uses up to 5 gigabytes with the 800 gigabyte file system, but it doesn't scale more than, it scales sublinearly.
Okay, and probably by the number of inodes or outstanding work items or some dynamic number. Because I remember from repair checker development, and I think you had some of this of your slides, is very often the file system size itself is relatively insignificant, while the number of inodes, be that regular files or directories, is actually often the annoying scaling factor.
Yes, exactly. So it doesn't really matter how big your file system is. What really matters is what kind of disk you're using and how much of the metadata you're actually using, because that's the metadata that has to be checked.
Ted?
Yeah, I mean, I think one of the things that you may find is that it's handling the corner cases, which is where all the complexity is. And so making something that works really fast for the happy path is usually not the hard part. The hard part comes when you actually have to do repairs. And the other observation I'll make is that for many of the workloads where I've had people complain about FSCK times, it's not taking, NVMe attached flash down from 300 seconds to 150 seconds. It's taking a big RAID array from 3 or 4 days to hopefully 2 or 3 hours, and so what you may find is that it's on the more traditional storage devices where a lot of customers have pain points. Because if you think about how much time it takes for a machine to reboot, between BIOS memory training and working with the cluster lock manager at the other end, it may be a good 15 minutes before a big node server is like back up in a cluster and serving. And so 100 seconds to 50 seconds is not actually the bottleneck. It's when it takes hours and hours on traditional storage where people tend to get cranky.
Right,
Yeah.
and this is why I think one of your future work items there is at least to me, very, very interesting, and that's the integration with online repair. I mean, with all the work Derek has been doing on XFS online repair, I think a lot of the algorithms here would fit in because people are more likely to use those kinds of features on modern SSDs, and so there might be some really interesting work there.
Yeah, definitely. Yeah, I know that for online repair, there's FSCK actually can do it online with LVM snapshots, right? So that's what the scrubbing mechanism does. But the one thing that I find interesting for those who care about LVM is that when we use LVM snapshots, there's a major performance deterioration, right? And that kind of inhibits the amount of speed that we can get out of the checking, right? Or it may inhibit the amount of performance you get out of other co-running IO-intensive applications, right?
So one thing that's interesting, and this has always been a bit of an issue with the academic work, is that you guys often sit on older releases, and there's some interesting performance work going on with the LVM snapshots, so you might want to look into that.
Okay, yeah.
And I mean, the other project, the XFS online repair, that's actually kernel code that sits in the file system itself, so it doesn't need snapshots or anything, and this is why a lot of these algorithms might be very interesting in that use case, especially as the kernel has really nice mechanisms like work queues for concurrent execution that could plug into this.
Okay, yeah, that's great. I'll take that into consideration.
All right, thank you. Thanks again, David. So